But now we are rotating on a sphere. So the only way we can actually represent this is now to have 4 pi, because we are looking at the
With
looking for the listening.
yeah.
For listening. For listening.
It's not a circle as such, but it's a 3-dimensional object. If I'm going to radiate only here, I can talk of 2 pi.
Yes.
Okay, but the signal which I'm sending from here is actually is covering the whole of this area. It's just like now we are having this water. Instead of supposing this water was your signal, okay, then it is actually covering the whole of this part. So if we are to look for the surface area, we will be talking of 4 pi r squared, isn't it? Instead of just talking of pi squared, we'll be talking of 4 pi r squared. Okay. Are we together? We are looking at a 3-dimensional figure. When you are sending out your signal, you are not sending it out now to a plane. It's not 2-dimensional. It's now 3-dimensional. Okay. So we are looking at the circumference. In fact, the circumference of that 3-dimensional figure. The circumference of a circle is 2 pi r, isn't it? The circumference of a sphere is 4 pi r. So that is what we are looking at. So think of it as a solid object, not a plate. So angle is an angle in 3 dimensions.
جد طبخ في بير مجلود ولا كده؟
Are we together or we are getting confused? I think I may go and get something which actually can show you like a pyramid. If I had a pyramid, then you have seen the shape of a pyramid, the way it is. Now look at the angle of the pyramid, at the center of the pyramid. That is actually a solid angle. We normally refer to it as a solid angle. And now we deal with them in star radians, because you have got each side is coming with its own angle. So 60 degrees, and then you have got the one at the center. So that is, and that because now when you are dealing with a sphere, you are dealing with something like 4 circles. Each one of them is having its own, and if they are all coming from the same center, then we can look at them. So this is basically what it is. This is going to be F, the angle, and then this one is going to be the Q, the horizontal and the vertical beam width. But now they are not using it in meters, but they are saying in radians. And then on the ground, then the controller will have the display. Okay. Now the display, what they are saying, it comes in many forms. What they are using, what actually is being explained here is quite an old form, where we used to have the scans, what we are referring to as air scans. These are things which electrons were being pulled using you have the cathode producing and the anode pulling. So we had very big screens, okay, and then we had electrons hitting the screen, and this is what gave you the image you are seeing. So these are the things which you are calling the scan. Then there could be rotation. The rotation of the aerial, as the aerial rotates, then you could see how the signal is moving. And it could give you an indication of a reflection. Because if there is a reflection, then the electrons would hit with more strength on the screen. And this will give a very bright signal on the screen, which you would see. But what they are trying to tell us here is that this scan did not give you the direction. Then the vertical axis is the strength of the return, and the horizontal axis is the time delay or range. Okay, it was giving you the distance the signal is from where you are. So you have got the signal rotating, you have got the radar rotating, and then depending on how far the signal is, it will give you the distance. And it was calibrated such that when the signal is, when the scan is on the north, it actually refreshes. Okay, every time the aerial passes the north, it refreshes on your screen. Actually, let us think about it. What is happening here? What is happening is that every time the radar looks at her lead, we are assuming the radar is stationary. Okay.
Stationary.
Yes, and then it moves. So how can we calculate the number of times the radar has moved? If we use her lead as our object, and therefore we use a lead as our reference, then we can say that every time the scanner faces a lead, we count 1.
Yes.
Okay, yeah. So we can start, and then we go round.
1.
Then we say 1. We go round again. 2, 3. But how will we know that the scanner has reached a lead? Okay, we must do something to our counting to ensure that when the scanner reaches a lead, then something happens.
By the horizontal signal, that is the delay.
By the delay, and also by refreshing of the signal. In fact, in your displays, there is a refreshing. So you find that when the signal passes the north, okay, there is a north signal coming on.
Frequency.
Yes, showing you that there is now a new scan which is coming on. Yes. So every time the scanner passes the north, a beam comes on the screen. You can see a beam on the screen. Then it goes around again, then another beam. So the scan rate is also very important because it determines how far you want your beam to go before detection. The maximum range your beam can go before the detection, the maximum range your beam can go. You can detect anywhere in between, but what is the maximum after which I cannot detect at all? That one will depend on the scan rate. So if I have got a very short scan rate, which also means that I've got a shorter wavelength, then I can only see at shorter distances. But if I've got a long scan rate, which means that I've got a longer wavelength, then I'm now able to see at further distances. Does it mean I cannot see at shorter distances? No. It only means that my radar range is longer. If I say that my radar range is 200 nautical miles, it does not mean that I cannot see 150 nautical miles. I can see 150 nautical miles. But what I'm saying is that the maximum range I can see is 200. So when somebody says that my radar range is 100 nautical miles, what it means is that they cannot see 150.
Yeah.
Yes. But they can see anything from 100 downwards. Now, if I'm going to see 200 nautical miles, then my scan rate has to be lower than this person who can see only up to 100 nautical miles. if this person is scanning at 15 revolutions per minute, I need to scan at about 10, because my signal has to travel that far and come back for me to see. Okay. So these are the things which you do when you are doing design. You do those calculations.
The APC sometimes uses a ground-based radar surveillance system to automatically monitor the location of all aircraft within the control area without cluttering up the radio communication channels. With this information constantly displayed on the ATC radar scope, the controller is able to make timely decisions regarding handing over aircraft to
This is telling us is that we are using, in fact, what they are talking about here is a primary radar now.
Yes.
Yes, they are saying that the ATC center uses a ground-based radar surveillance system, which can be the ground-based the surveillance system we can have. We can have the PSR, the primary surveillance. We can also have the second surveillance, the still ground-based. We can have the monopass, even the models, they are still ground-based. But what is important for us here is that you use these systems to automatically monitor the location of all aircraft within your control area. The whole idea is that you monitor this such that you don't have to clutter the radio communication. What do I mean? Let's look at a position where we are doing procedural control. When you are doing procedural control, you have got 3 aircrafts in your airspace. So it means that every time you have to communicate with the 3 of them at the same time. At one time, you are communicating with this one on the frequency. Then immediately after that, you have to communicate with another one. Okay. So actually, your radio frequency is constantly on use, and sometimes one of them would be wanting to communicate with you, but they cannot because you are communicating with another. So you have to have them on hold as you communicate with the other person. Now, this is reduced when you are using radar, because when you are using radar, you are able to see the aircrafts which you have.
No need to communicate all times.
You don't need to communicate all time. You only communicate to them when there is need. Like, let's say somebody is deviating. You had agreed that they are going to travel in this direction, but you can see that they are not following their flight plan. They are going in a direction which you did not intend. So you can now call them and tell them that, okay, well, this is what we agreed, but you are now not doing the correct thing. So your communication frequencies then are actually utilized in a way that they are not congested. Actually, that is what this statement means. But it's something also which is important for us. With this information constantly displayed on the ATC radar scope, the controller is able to make timely decisions regarding handing over. Like, you are looking at the aircraft coming, and you know very well that when they reach a certain distance, you are supposed to hand over to either the area controller or the tower controller. So at that particular time, you are able to hand over. Actually, your workload is more or less minimized, because now what you are doing is doing monitoring, more or less. You are monitoring the movement of these aircraft in your airspace. And it's only when you see something which requires interjection that actually you talk, you take charge. So that one happens. So to approach your departure control center, you can also vector aircraft to avoid collision in courses, because you can see them. Okay, you can see how they are moving and you can tell them, no, when you are doing that, it's not correct, so follow this routine, and then you can maintain safe altitude separation between aircraft and locating the attacking aircraft. So with radars or with surveillance, the air traffic controller has got a better situational awareness of their airspace. You are seeing all your aircrafts, okay? You are monitoring their movements. It is only, and you have got time. You have got enough time to talk to them in case there is some confusion, some limitation. Okay.
The ground-based ATC by transmitting a beam of energy which is reflected from the aircraft and returned to the PSR antenna. Reply signal back to SSR system. Data received from the PSR and SSR are used in conjunction to develop local air traffic situation display on a controller radar scope. This enables
Over PSR, we are having a beam sent into space, reflected, comes back, and this one gives us the location of an presence of an aircraft and the location. But then there is some limitations. There are problems with that, with the PSR. There are several limitations which we are going to see later. So they came up with an idea which was better, where actually the SSR, the military came up with an idea where they were identifying you, are you an enemy or a friend? So they normally refer to it as identification, friend, or foe, IFF. Now this later came to be used in the civil space. So these are the ones which are now calling SSR. Well, with the SSR, we send codes, we send interrogations from ground, and then the aircraft responds to them. So what you have got on the ground is what we call an interrogator. What you have got in the aircraft and is what we call a transponder. It means it is a transmitter responder. It's a transmitter that responds. So you have got an interrogator asking questions, and then in the aircraft you have got a responder, something that responds by transmitting signals. Okay. So we have a transponder. So let's continue and then and go to
radar surveillance system operation. There are two types of radar system installed each ATC ground station. The first called primary surveillance radar.
In the airport.
No, it's the radar. The distance actually, what they mean is the range. If I'm going to have a terminal radar, then within that area, the amount of aircrafts which I'm going to see are very many. So I want rapid returns. I want rapid returns. Because I want rapid returns, I should have a higher scan rate. Because the scan rate is the number of times the radar goes round per minute. So if I've got very many aircrafts, I need as many rounds as possible, because the aircrafts are coming in, and I need better information. Now, like the ground radar. Ground radar is very fast. It's not even 10. It's a very fast radar, okay? The one which you have at the airport terminal. But now approach radar should be faster than area radar.
Yes.
Yeah, that's what it means. So as I come towards the airport, the speed of my radar, my distance towards as my control towards the airport comes closer, the speed of my radar should be
High quality.
faster.
High
The range
quality,
is lower.
Yeah?
The range is lower in the terminal.
but
Yes.
high quality.
All of them should have high quality. The integrity of your radar is very, very, very important. So when you are doing design, we talk of integrity. Okay. And some of you are going to do design because you are going to be
To use it.
in charge of ANS. When you are in charge of ANS, You're the one who says what type of radar you want.
You have to know this to answer that.
Yeah?
For procedure design, or what to design.
Design the radar.
Now, when you want to buy a radar, like now, let's suppose in Khartoum, they want to buy radar.